Section 3 from Unit 2 is on atomic structure, so it's going to talk about parts of an atom as well as the experiments that led to the discovery of those parts of an atom. Let's start with the definition. An atom is the smallest particle of an element that retains the properties of the element. Okay, so if you go any smaller than that, it stops behaving like that particular element. They are incredibly tiny, and so just to try to give you some idea of scale here, if we took an atom, okay, and for this sake I've got it as a single dot here, but it would be considerably smaller than that, obviously. Let's say we took an atom and blew it up to the size of an orange. Okay, so we kind of understand what the size of an orange is. All right, and for the sake of consistency, I just drew a little dot there so you can see how much bigger just this image is. Now, obviously, this dot would be even smaller than that. But if you took an atom and blew it up to the size of the orange, for things to remain relatively the same size, an orange would have to balloon up to the size of the entire Earth. Okay, so that's how much larger, how many times larger these things are, right, in terms of relative scale. If you took an atom and blew it up to the size of an orange, the orange would have to get as big as the Earth to stay on the same scale. So it gives you hopefully a sense of just how small an atom actually is. When it comes to actually looking at atoms, we can't actually see them. We have some tools to help us visualize where they might be. One of those is called a scanning tunneling microscope, STM. You don't actually see atoms, but you can get visual representations of their locations and their size. This is what the picture over here is what this looks like. Okay, so you're not actually seeing a picture of an atom, but you're seeing a computer's rendition of, okay, this is where this atom is, and this is its approximate size relative to the stuff around it. Okay, we do have the ability to come in here now and move atoms around, okay, and even parts of an atom. Right, this is nanotechnology. This is currently kind of where science is heading, is seeing what parts of this can we move or take out. But the reason we can't actually see it is interesting. It's because the diameter of an atom is somewhere on the range of 10 to the negative 10th meters, okay, which is also angstroms, if you've ever heard of that unit before. But wavelengths of visible light, okay, if we take this entire wavelength here of visible light, it's on the order of 10 to the negative 9th meters, or nanometers is generally how it's measured, which means that visible light is actually larger than the size of an atom. So you can't see it. Your eyeball can only pick up visible light. Okay, and if we use a light microscope, microscopes only work with visible light. So we have to come up with some other type of technology to help us visualize it, and that's why we can't actually physically see an atom. Okay, so John Dalton's theory in 1803, atomic theory, proposes the idea of atoms. We know atoms exist, so now what? So that was 1803. Well, in the 1880s, scientists, chemists, and physicists are starting to play around with these devices called cathode ray tubes. Okay, kind of looks like this guy right here. And essentially what you would do is you had a cathode and an anode, and this tube here was vacuumed out, so there's no atoms or anything inside of it. Okay, it's empty. There's no gas. It's just a vacuum, right? Okay, like space, outer space. Okay, and you hook this thing up to some sort of electrical source, battery, okay, and then you would complete the circuit here, and what we would get is actually you'd see a beam going from one side to the other, okay, and these are called cathode rays. Okay, you see this beam go from one side to the other. They called them cathode rays, and that's why these are called cathode ray tubes, because they're coming from the cathode side of things. The rays must have a negative charge. We'll talk about how they knew that here in a minute. Okay, they didn't know the exact value of this charge, but they also determined that the rays must exist in all forms of matter. So if you changed what these, as long as you used metal here, since we're talking about electric current, but if you changed what these were made out of, we were still getting this beam coming across here. So it must exist in all forms of matter. We know it's negatively charged. We weren't sure of the exact charge. Okay. So how did we know it was negative? Well, two ways. The first is we took a magnet, okay, with the north and south pole on it, and we put the magnet around the beam to see where it was going, and it would bend towards the north end of the magnet, which is the positive end. And if you know anything about charges and attractions, opposite charges attract. So if it's bending towards the positive side, that means the beam itself must be negative. Okay, opposite charges attract. So it's bending towards the north end of the magnet, so we know that this beam is negatively charged. So we know it's in everything. We know it's negatively charged. We're not quite sure of the exact value of the charge yet, though. Another thing we could do is test it with electrically charged plates. Okay, so not a magnet, but we charge up the plates, and it would bend towards the positively charged plate. So that's how we knew that this was a negatively charged beam. And by the way, if you haven't heard about this before, cathode rays would later go on to form the first black and white televisions. In fact, if you've got an old TV at home, like an old rear projection TV from 20 years ago or more now, if you take a magnet to it, much like what we do over here, if you take a magnet to it, even the color ones, you'll distort the surface of it. It will change color, kind of a pretty rainbow color. I mean, it looks really cool, but I imagine if you did it back in the day, your parents might be very upset with you for ruining their television. But the first televisions, the black and white televisions, were made by cathode rays. Okay, so these beams would hit the surface there and turn the pixel either on or off, and then you would see that as an image. So that's where these things actually became used about 60, 70 years later in the formation of early televisions. Okay, so we know that cathode rays exist. We know they're negatively charged. We know they're in everything. The question becomes, how did scientists determine the charge of an electron? So the first thing that you need to do that is determine the charge to mass ratio. You need to figure out what's the overall charge on this beam and what's the mass of this beam. Okay, and the first person to do that was a British physicist named J.J. Thompson. Okay, this is in the 1890s. He figures out the charge to mass ratio, okay, of the entire beam. He's going to have a very controversial conclusion here. So he determines that the mass of the charged particle was much less than a hydrogen atom, which was the smallest atom. And if you remember from John Dalton, right, he said that the smallest particle in the world is an atom, that nothing can be smaller than that. And Thomson's conclusion here, part of it, is that whatever this thing is, whatever this negatively charged bit is, okay, is smaller than a hydrogen atom. So he's immediately contradicting Dalton's theory, which at this point was basically chemistry canon. Okay, so he's actually going to get kind of laughed at when he suggests this, because of course there can't be anything smaller than an atom. We've known that since 1803. So he's not going to be taken seriously at first, but he's definitely going to turn out to be correct. So Thomson found the charge to mass ratio, but he didn't find the charge or individual mass of what we're going to end up calling an electron. Okay, he didn't determine the individual one of that, but he did have a charge to mass ratio. The actual numbers come from an American scientist named Robert Millikan. This is in the 1910s. And his famous experiment, which you should know the name of, is called the oil drop experiment. I think his device is still in a museum somewhere, because it still functions if you were to test it. But he's actually going to be the one to determine the charge and mass of an electron. Okay, and he's using this oil drop experiment, which we'll talk about here in just a second. But he determines the charge on it is 1.602 times 10 to the negative 19th coulombs. So not a very strong charge, but it is negative. And if you know the charge to mass ratio from Thompson, and you know the charge, well, then you can find the mass. And he determined the mass to be 9.1 times 10 to the negative 31st kilograms. It's an incredibly tiny number. And that's also about 1/1840th of a hydrogen atom. Okay, so this is going to back up Thomson's findings that there is something smaller than a hydrogen atom, and not only smaller, but considerably smaller, right? It's only about 1/2000th or so the mass. So what's the other 1,839 parts of it? Well, we'll get to that here in a minute. But let's look at this experiment. This is called the oil drop experiment. So basically, what we're starting with here is like the world's finest perfume mister. Okay, so we've got an oil in here. That's what the oil is coming from in the oil drop. And it's basically like those, perfume bottles with a little sprayer, except it creates a very, very fine mist. And when those oil droplets land on the positively charged plate, any sort of chance of there being extra negative charge on it is going to be picked up by this plate. The drops are going to fall through that positively charged plate, where they're going to be hit by radiation, X-rays, okay? Again, just all trying to eliminate that charge, anything that's left on there, and to try to atomize these drops, okay, so that they're just a single unit by themselves. And then it lands on the negatively charged plate. And then what he could do is he could figure out, well, how much mass did a droplet gain and how much charge did a droplet gain. And if he could do it as a one-to-one, just a single unit of the oil, picking up a single negatively charged particle, he could figure that out. The amazing thing is he did this, in the 1910s or so, early 1910s, without a calculator, without computers, and he came within, I think 99% of the correct value of what we use today. So an incredibly remarkable experiment for its time. Okay, just because we discovered electrons does not mean that the problems were all solved. There were two questions that arose. As soon as we knew electrons existed and we knew their mass and their charge, here are the questions. Number one, if they have a negative charge, if atoms have a negative charge, why does matter have no net charge? Okay, you and I are not negatively charged because if everything was negatively charged, nothing would stick together, right? Like charges repel. So all these charges would be moving away from each other. So if there's negative charge in matter, why isn't everything negatively charged? It means there's got to be some positive charge somewhere to balance this out. And then question number two, if their mass is so small, what accounts for most of the mass of an atom? Remember, the electron was only 1/1840th of a hydrogen atom. So what's the other 1,839 parts of it, right? Where's the rest of the mass? And where's the rest of the charge, the positive charge? Okay. So the first suggestion of what an atom might look like comes from J.J. Thompson, the same guy with the cathode ray tubes. And he proposes what's called the plum pudding model, which is about as thoroughly British as I can possibly imagine. Essentially what he's saying here is that the plums are going to be like the electrons, okay, and the pudding part is just a positively charged, kind of like a gel or a goo, okay. And so this is what it would look like over here. That these pudding, by the way, if you've never had fruit pudding, okay, you've got fruit dropped into the pudding, okay. So he's saying that these electrons in here are negatively charged. They're like the fruit. They're dropped into the pudding, which is just the positively charged gel that these negatively charged things are suspended in. And he's trying to explain here, okay, this is the positive charge, right? All this space in here is the positive charge, evenly distributed positive charge, all right? Not that they're particles, it's just a gel, okay? He's saying that all of that is positively charged. And that's hopefully also explaining what the rest of the mass is. Okay, so that's his goal. So Thompson proposes the plum pudding model. The next thing you have to do when you propose a model is you need to test it or have somebody test it to see does it check out. And so this experiment here, this is done in 1911. This is done by Ernest Rutherford. He's actually a New Zealand scientist, so not a whole lot of those that became famous. And his job was to test the plum pudding model, and we'll explain what he did here in just a moment. He didn't set out to disprove the plum pudding model, okay? That was not his goal, but he ends up disproving it. All right, as we say in science, you can always offer support for things, but you can't prove it, and you can disprove it. Well, he disproves this. And his experiment's called the gold foil experiment. So we have the oil drop experiment from Millikan, and we have the gold foil experiment from Rutherford. Okay, so he is going to come up with an experiment to test this. So here's what he says. He says, okay, let's take a model, the plum pudding model of the atom. All right, and if this is the case, I am going to shoot what he's going to call alpha particles, or what are called alpha particles, at it. And if this is true, alpha particles, by the way, they're smaller than atoms. We knew that they existed. It's basically a type of radiation. And that as these alpha particles would pass through an atom, they should go straight through, okay, as they pass through atoms. They might hit an electron on the way through, like ever so slightly, like right here, and you get a slight deflection, or right here, where you get a couple of slight deflections. But in general, based on my setup here, all these alpha particles, okay, are going to pass directly through the atom without any deflection. All right, we should get every one of them to pass through with maybe a very, very, very slight angle of deflection. But essentially, if this is all just goo and positively charged goo and these negatively charged, very small electrons, remember the electrons are very light, they shouldn't have enough power to deflect anything. Okay, if you know anything about the equation for momentum, this should not deflect anything massively. If anything, alpha particles should be pushing these things out of the way as they pass through, based on this model. So here's his setup. He's got his beam of alpha particles, and the atoms he chooses to shoot them at are gold atoms. Gold, by the way, you can hammer into the thinnest sheet of foil. I want to say you can get it as thin as like 79 atoms or something like that. An insanely thin sheet of gold foil. But he shoots the alpha particles at it. And based on his expectation, okay, we should get 100% of them hitting his detector over here. All right? So that's what we should expect. Well, when he turns it on, he finds out that just about all of them go straight through. It's something like, 19,999 out of 20,000 particles hit straight on. But a very few of them have a slight deflection. Some of them have a pretty strong deflection. And then actually he gets a few of them that get shot backwards all the way back towards this box. So not only did it hit the gold foil, but then it went straight backwards. And essentially, these electrons are so light, we shouldn't get any major deflections, okay? We shouldn't be getting anything that's going here, hitting an electron and then bouncing off like that, or hitting an electron and basically going immediately backwards. Okay, everything should be going straight through, and it should move the electrons out of the way, because these alpha particles are heavier than these electrons. So he's going to have to say that this model has to be incorrect, because there's no way to explain these extreme deflections based on the plum pudding model. So this gold foil experiment done by Ernest Rutherford is going to disprove Thompson's plum pudding model, and now Rutherford is tasked with coming up with an explanation that tells us why did these alpha particles get such extreme deflections. So, plum pudding model is not correct. Most particles pass through, some deflected at small angles, others at large angles, and others directly back at the source. So the conclusions here are that atoms were actually mostly empty space. If you've got something like 99, 0.999 something percent of them passing straight through, well then, okay, we're assuming that most of those are empty space. Those alpha particles just went directly through an atom. It's that one in every so often rare chance, okay, that it hits and has a strong deflection. So how is it able to deflect? Well, you need something in there in the middle of the atom, okay, that is very dense, so it means it's very heavy and very small, that could actually deflect these alpha particles. Okay, it needs to be heavy. If it's not heavy enough, this thing just gets pushed out of the way, right? So all the positive charge and most of the atom's mass is located in what he calls the nucleus. So now we have this center of the atom here, okay, called the nucleus, that is extremely dense, right? Most of these particles are just going to keep passing right through without accidentally hitting the nucleus. And obviously this is not to scale, because this would just be like a singular point in here. But every once in a while, you might have those alpha particles hit this nucleus inside of the atom. And this thing is heavy enough to not get flung out of the way. It's heavy enough to cause these extreme deflections, okay? And then lastly, electrons are held around the atom by the positive charge in the middle. So if we've got, our nucleus here in the middle with the positive charge, all right, as these electrons move around the nucleus, they're being held towards the center of the atom. Change color here. They're being held towards the center of the atom by its positive charge. Okay, so it keeps these electrons from just flying away. Okay, so what do we know about the nucleus based on Rutherford's experiment? Well, we know it occupies a small space, but contains almost all the mass. Therefore, the nucleus is very dense. Remember, our equation for density is mass over volume. Well, what we're saying here is that this number, mass, is really big and volume is really small. Well, if you have a big number divided by a really small number, that's going to give you an even bigger number. Okay, so the density here is very, very high. What else do we know about it? Well, if an atom had the diameter of 2 football fields, so 600-foot diameter here, kind of sketch this out to show you, the nucleus would be the size of a nickel. So imagine if you took 2 football fields from end to end and then drew a circle with that diameter, okay? the nucleus would be sitting here in the middle of all of that. It would be the size of a nickel. So imagine you've got, 300 feet this way, 300 feet this way, and all the way around in a circle. A single nickel in the middle of that would be the size of the nucleus. So all the rest of this is just that empty space that we're talking about. We said atoms are mostly empty space. Imagine how much empty space there is. All there is just one nickel there in the middle. And that also explains Rutherford's results, right? Most of the stuff is just passing right through. If you were playing on, 2 football fields and you had a single nickel somewhere on the field, there's a slight chance at some point during a football game somebody might step on it, but there's not a guarantee, okay, because the football field's a lot of space. So, yeah, all the rest of this is just empty space. There's still one question left, and that is there's still some mass that we don't have explained. Obviously, this is going to go on to get us to talk about what protons are. Rutherford's going to suggest protons and find the mass of a proton. There's still one more thing left because there's still some mass left that we haven't explained. Okay, so in 1920, Rutherford's going to refine the concept of a nucleus to include protons. So these are subatomic particles carrying a charge equal but opposite that of an electron. Okay, so they have the exact opposite charge of an electron. What we're going to find out, though, is that if you think about it, if we've got these electrons traveling around the outside of a nucleus, right, and let's say the nucleus has got, if it's 4 electrons and 4 protons, I put a lot of positive charge together here in the middle. How is this able to stick together since we know like charges repel? So we needed a couple of things here to explain what's going on. One, how is this positive charge able to stick together without immediately just bursting apart because of the charges repelling? And 2, there's still some more mass somewhere in this atom that we have not figured out. And that comes from James Chadwick. So this is 1932. He solves the mystery of the remaining mass. He says, okay, somewhere else inside of this nucleus are neutrons. All right? And their job is twofold. One, it gives the nucleus a little bit more mass, and 2, it's going to allow for some spacing between these protons so that the positive charges aren't literally right on top of each other. Okay, so a neutron is a subatomic particle that has a mass nearly equal to that of a proton but carries no electric charge. So there is no positive or negative charge to neutrons. They're there to space out the nucleus a little bit more and to give it its final mass. That was the last bit of mass we needed to solve for. Okay, so putting this all together, atoms are composed of 3 subatomic particles. If you hear the term subatomic particles, don't panic. Sub just means smaller than, and atomic meaning atom, so smaller than an atom particles, electrons, protons, and neutrons. Atoms are spherically shaped. They have a small, dense nucleus at the center where all the positive charge is. The electron cloud surrounds the nucleus. It's held together by the positive charge in the nucleus. The nucleus is composed of protons and neutrons, right? The electrons are going around the outside of that. The nucleus is 99.97% the mass of an atom, and it occupies 1/10,000th of the space. So lots of mass, low on the space there. So very, very dense. And the other thing we need to note here is that neutral atoms have equal numbers of protons and electrons. Since they have equal charges, okay, equal and opposite charges, for an atom to be neutral, however many electrons I have, I must have the same number of protons. Here's just a good picture of what this looks like. So here would be like the whole picture of an atom. Okay, this would be your electron cloud. The electrons are somewhere out here. The nucleus is this tiny, dense part in the middle. Very, very small. It's made out of protons and neutrons. So this is a zoomed-in picture here of the nucleus. This is just a good summary chart for your notes, so you can screenshot this just to remember where things are.